Okay, so today we are starting with chapter 3, which is about real forms and involutive automorphisms. So basically, in chapter 2, we saw that there is a one-to-one correspondence between conjugacy classes of real structures of a complex Lie algebra V by inner automorphisms and isometry sorry, not isometry isomorphism classes of real forms of E, right? So if we have a real structure of our...
Sorry, why by inner automorphisms?
Isn't it by inner automorphisms?
It's not just automorphism.
Okay.
It's a question. I think it's automorphism. This is what proposition 1 said.
Yes. Okay, so maybe I will just put this. Okay.
Otherwise, maybe it's not 1-to-1.
Yeah.
Well, I guess you either put both inner on the left and on the right, or neither, right?
Sorry?
I mean, you can put inner both on the left and on the right, and it would be a one-to-one correspondence, or you can emit it both on the left and on the right. So it's not you can't just put it like on the left but not on the right. I think.
What does it mean to be an inner isomorphism? Doesn't make sense there on the right, right?
Well, something like two real forms are isomorphic by an inner automorphism of G if they are carried.
So they are conjugate, right?
Well, yeah, I mean that's.
Yeah. So maybe if you put here inner.
Yeah, we don't know that. Yeah.
I'm not sure, but maybe if you put here inner, then
Yeah, that's
conjugate by an inner automorphism.
Yeah.
So yeah, basically what we did is we take here a complex structure or yes, then here. Well, I'm not going to take classes. Basically, for a complex structure, real structure, we take its set of fixed points, and that is a real form of the Lie algebra. And conversely, if we have a real form G0 and two complex structures were conjugate, then we have that the corresponding real forms were also conjugate, I think. And if we take a real form, then we can define an isomorphism for an anti-evolution here. By just taking x plus iy to x minus iy. And this is a real form, and it turns out that if two real forms of E are isomorphic, then these maps are conjugate, right? So the aim of this chapter is to prove that here we can substitute the word real form by, recall that real form is just an anti-evolution of the algebra for evolution. Here we can say inner automorphisms and the same here. And you can see classes of evolutions of G by inner and how we are going to do that. So basically, there's like 5 steps to, or 4 steps to do this. So the first step, well, this is just to read if this is semi-simple, not in generic place. So the first step is to show that every semi-simple real algebra admits a compact real form or a compact real structure. And in fact, later we will see that this real structure, which will in the beginning just be constructed as we did in the previous week, composing the split real structure and the Weyl evolution of our semi-simple algebra, is not, there's not just one, but it is also this compact form is unique up to inner automorphisms. It is also unique up to automorphisms. Obviously. Using this, we will construct a map. We will call this tau. We will consider a map sending a real form sigma tau structure. Real structure sigma to sigma tau, which in principle might not need be an involution, but in the case that sigma commutes with tau, this will be right because you just move things around and you have sigma tau sigma. So this is an evolution. If you compose it with tau again, then you will get always a real form which is the sigma you started with. Then we will show that for any real structure, there exists an inner automorphism by conjugating by this inner automorphism, we get a new real structure that commutes with that. And then the last step is to construct our one-to-one correspondence follows. If you take sigma, then you can always choose a representative of its conjugacy class by an automorphism, which commutes with that. Then by the previous point, you have that sigma prime tau. It's an evolution. And then you take conjugacy classes. This gives the desired correspondence, and not only that, but this correspondence does not depend on the choice of that. Right? So today, I guess we will just be doing the first part of this construction, and maybe we will start introducing things necessary for the second one, which is that if G is semi-simple, then there exists a compact relation. And then we will give examples of such compact real form in excellency. So how do we do this? Basically, we are going to construct an inner product. Well, not an inner product. It's an Hermitian form on G, which will be compact if well, our set of fixed points will be compact. These Hermitian forms depend on the real structure that we are taking. And our set of fixed points, our real form, will be compact if and only if this bilinear form is positive definite. So basically, let's sigma be a real structure. And define H sigma of x, y by minus the killing form of x sigma y. So this is similar to how you construct the inner product on a semi-simple non-compact real algebra. Right. Then H sigma is the linear form. Okay, and this is easy to prove because linearity just follows from the linearity of the clean form. So this is minus b c1 x1 plus c2 x1. You take the scalars out, then you have that this is minus h sigma of x1, sorry, c1 h sigma of x1 plus c2 h sigma of x2. And the fact that it is Hermitian still follows from the fact that if we have a real structure and we put it inside our killing form, then the killing form of sigma x, sigma y is just the conjugate of sigma x, the killing form of xy, right? So it's sigma of xy minus the killing form of x sigma y, but this is minus the conjugate of the killing form of sigma x, sigma square y. But this is a real structure, so sigma square is the identity. Here we have this, and just by symmetry of the killing form, we have that this is minus the conjugate of sigma y, right? So it is Hermitian, and now we have a proposition that tells us about some properties of this inner product, of the candidate to inner product, which is the following. The gamma is an automorphism of the commuting with sigma, then it is an isomorphy for x. Also, H sigma, it's an invariant for the elements on the set of fixed points of sigma. That means that if the fixed point for sigma, then H sigma of x bracket u is minus H sigma of u comma xp for all u. And lastly, that H sigma is positive definite. If and only if the set of fixed points of sigma is a compact. So the proof of this is not difficult. The first one is because if we have an automorphism of G computed with sigma, then it's sigma of gamma x gamma y. It's just minus the given form of gamma x sigma gamma y. Now we use that sigma and gamma commute. So we have minus the given form of gamma x gamma of sigma y. But then the given form is invariant by automorphisms. So this is just minus b x sigma y. This is x sigma. Second one is also easy because we have the properties of the given form. So it's sigma of x bracket u comma b is just minus b of x bracket u comma sigma b. But then we know that the given form is an invariant, so we can take this to the other side by changing sign. So this is b u comma bracket of x with sigma b. But x is a fixed point for sigma, so this is the same of writing here sigma x, and sigma is a real form, so it preserves the bracket. So this is b of u sigma of x bracket u, which is just minus h sigma of u. And the last one is because we know that fixed sigma, sorry, again, something. Oh yeah, here I'm missing a thing, that is that H sigma restricted to fixed points of sigma is just minus the given form, and therefore this positive definite. If only if it's a convection algebra. This is because H sigma is restricted to fxy where fxy are fixed points for sigma. This is the same as minus b plus sigma y, but this is minus b. So we know that subalgebra is compact if only if its given form is negative definite. Then we have that fixed sigma. It's compact if b negative definite. sigma, which is the same as saying that H sigma, which is minus B, is negative definite on fixed sigma. But now fixed sigma is a real structure. H sub sigma is an emitting linear form.
Sorry, do you mean H sigma is minus B is positive definite? Is it positive or?
Oh, yeah, sorry, yes. But if we have a real structure of a linear form, well, sorry, an emitting linear form, which is definitely positive of the real structure, then it has to be definitely positive of the whole space. So then we have H sigma is positive. This will be used to show that the real form that we are going to construct now is compact. Because it will be easy to show that this form is positive. So now,
Can I ask a question?
yeah.
Where do we get the implication that if the fixed points of algebra of sigma is compact as a Lie algebra, then the killing form of G is negative definite on it? Is it trivial?
Was a proposition on.
Right? Yeah, so can you state the question again?
So on the right hand side, there is this fixed sigma is compact implies that B is negative definite on fixed sigma. Is it obvious?
That's because fixed sigma is a real form.
Yeah,
and G is
yeah.
semi-simple. So
No,
G here is just a complex of algebra.
It's not because of that. It's because if you restrict, it's like it happens with ideals. That if you have an ideal of the algebra, then the killing form restricted to the ideal is exactly the killing form.
Yes, but this is not.
We have a similar property here for real forms.
Yeah, but even if there is like pretty much no difference between the restriction of the ambient killing form to fixed sigma and the killing form of fixed sigma, still, I mean, what do you mean by saying that fixed sigma is compact? Do you mean that it's just compact as a Lie algebra?
Yeah.
Yeah, but I mean, compact. I thought that compact Lie algebras are characterized by the property that their killing form is negative semi-definite. I mean, you can have something like something compact semi-simple plus something abelian. It's also regarded as compact, right?
Yeah, you have something abelian also. Yeah.
I think you have to assume that G is semi-simple, because if B is negative definite there, then this means that fixed sigma is semi-simple, but it's a real
Oh, yeah,
form.
okay. Yeah.
So I think you have to assume from the very beginning that G is semi-simple.
Yeah. So okay, we are pretty much using the fact that G is semi-simple at like every step. I see.
But I thought you didn't need it then. But
Why do you say that? Why do you say that you have to assume that?
So if B is negative definite on fixed sigma, then fixed sigma is semi-simple.
Yeah, that's true.
But fixed sigma is a real form of G. So fixed sigma being semi-simple implies that G is semi-simple.
Yes, this is true.
So that's something that you prove later. You don't have to assume from the beginning that G is semi-simple, I guess.
No, but like again, if you don't assume that G is semi-simple, then you cannot deduce that fixed sigma is semi-simple, So in general, from the fact that fixed sigma is compact, you only get that B is negative semi-definite on it, because there may be an abelian part to fixed sigma. So here in the first implication, you must assume that that fixed sigma is semi-simple, which is pretty much the same that assuming that G is semi-simple, right?
Well, I keep don't understand.
Doesn't it say at the beginning of the chapter something like that we're going to assume that G is always a complex semi-simple?
No. It just
I mean, this is clear, right?
Everything holds except for the last part.
But what it doesn't? What doesn't hold? What implication doesn't hold?
Fixed sigma is compact if and only if B is negative definite. That's not true. Fixed sigma is not semi-simple.
But it's not. Is
So the implication to the left is true. But compact semi-simple. That's the
okay. So it.
H sigma is positive definite,
Yeah.
then this is negative definite.
Yeah.
But this is the same as it's right because it is
Yeah.
it is a real form.
Yes.
So then we have a fixed sigma.
Fixed sigma is compact and semi-simple.
Mhm.
Not getting semi-simple here.
Yes, because B is not degenerate.
But that's something that you deduce later.
But the thing is that you deduce it later, but you cannot go backwards unless you assume semi-simplicity. So you only have an implication. Okay.
Yeah, but also like even in this implication, which kind of works anyway, if you assume that H sigma is positive definite, it implies that B is non-degenerate, which implies that G is
Okay. Then it was.
So I think the context of G semi-simple must be there.
Okay.
This sorry. Now I am still busy. So here you are proving the implication to the left, right?
Yeah.
You're okay. So for the right, to the right, what's the problem?
The problem is that if fixed sigma is compact, but not semi-simple, then you can't assert that B is negative definite. It's going to be negative semi-definite.
Okay.
That's the problem.
Yeah.
Yeah, that's right.
Okay.
So yeah, we have to add semi-simple there.
Okay, thanks.
Yeah. Think it will make no difference because we will always work with semi-simple algebras. Well, so
But maybe this is because Onishchik has a different definition of.
Yeah, that's not the break.
No, it's the same. He's still saying that the no, there is a mistake. Yeah. There is a mistake. Yeah, there's no hope. Yeah.
No, I mean, not that we're gonna use the situation where G is not semi-simple a lot, right? For us, it will mostly be semi-simple.
Oh, probably not.
No. I mean,
Yeah, so it's fine.
I was saying that we are going to assume that G is semi-simple from now on, but
Okay.
it doesn't make any difference if we say it before this proposition, right? So yeah, before this proposition, we say that G is semi-simple. I mean, clearly this was here all along, but we didn't notice it was written there. So yeah, we have a semi-simple algebra, and we are going to construct our compact real form. So recall that if we fix a maximal torus of algebra. On the Euler chamber. Then we have a system of canonical generators H I, E sub I, and F sub I, which satisfy some relations that are written on chapter 1, and we can consider its Cartan matrix, right? It turns out that if we take the same maximal torus of algebra as a subalgebra of a maximal torus of algebra of the conjugates subalgebra, the corresponding system of generators of the conjugate subalgebra is exactly the same one, right? So H I, E sub I, and F I. Obviously, the Cartan matrices are exactly the same because it only depended on the brackets of this, of the E sub i's with the F sub i's. So one has the following, that thus there exists an automorphism, oh, an isomorphism, sorry, which we are going to call sigma of E into G bar, which takes this canonical system of generators into this canonical system of generators of G bar, right? This was equivalent, having an isomorphism satisfying this, and the Cartan matrices being equal. That this is an anti-isomorphism of G. So such that sigma squared, it's identity, right? Because it takes this to this and then again, so it has to be. What this is called the split real structure of G with respect to D, right? So it only depends on the choice of the wind chapter. So this is what I said before to you, Ivan, that as wind chambers are conjugated by inner automorphisms, I suppose the corresponding real forms that you construct this way are also conjugated. So if you if you prove that every split real form is constructed this way, instead of giving in this definition, there you have a inconclusive proof.
Okay.
And similarly, fixing C as a maximal Doral subalgebra minus D as a wheel chamber. We have that. The corresponding system of generators is x to y, sorry, minus x to y, minus x to y, and minus x to y. And you can check this just by checking out that the corresponding bracket relations are the ones that they are supposed to be. It is also easy to see that the Cartan matrices inside, because know that the coefficients must satisfy this. Because these are like this is like sorry, x to y and we know that for Cartan matrices, sorry, for a canonical system of generation, generators, this is AJI. Yeah. This is the same as inside bracket Fi, but this is a canonical system of generators with respect to D. So we must have that this is minus, Fi. This is a canonical system of generators for D. So this is minus Ij, Fj. So just take so the coefficients must be the same, right? In the Cartan matrix. So thus we have an automorphism which we will call taking xi to minus xi, ei to minus fi, and fi to minus and this easy to see. If you follow this terms of the basis, hi underline square is of hi is hi, let's say for ei and fi. So it has to be an approach, which is called the evolution. Okay. With respect to this question, right? So if we fix a Willis chamber, we take this evolution, this real structure, this evolution, and they commute. We can check this on basis. It commutes with sigma. And thus, omega sigma or sigma omega is a real structure. Okay, which is our candidate to compact reals. It is antilinear because omega is linear and sigma is antilinear. And its square is identity because omega and sigma commute and both are involutive, right? And now we want to show that this is compact. And for this, we will prove superpositions beforehand. I will try to leave them here on this corner of the blackboard. So, proposition number 1. Oh, actually, it's proposition number 2, I think. Is that the restriction of tau to the real form of T is minus identity. The second fact is that tau of G alpha is G minus alpha. And proposition number 3, well, actually, might be doing proof first and then write here the other proposition. This is easy because if you the HI are a basis, real basis of the real form of T, and tau of HI is omega sigma HI, which is just omega HI, which is minus H. Right? That's minus is T of R minus I. Number 2, it's also easy because C alpha is the span of E alpha or any E alpha not 0. This is because complex root spaces are always one-dimensional. So if we take an H in T of R, then we have that this is the same as this, because tau is a real structure, and so it preserves brackets. But then tau is an involution, and tau of H is minus H. So A. So we have that this is minus H E alpha. and this is, oh sorry, not the square. That's right. Minus 3 of h e alpha, and then you take the outside. Right? Minus 1. This is because tau here is minus identity, so you can just put the minus sign and write tau and take it outside. You see that it is a real structure, but then this is a vector in G alpha, so we have that this is sorry, minus of h d alpha, and here you may have to take conjugation, because this is tau of alpha of h e alpha. This is minus tau this, and tau is anti-linear. This is minus. Okay, but h is in the real form of this, so it is a real number. So it's conjugated to yes. So now we have it's not 0. It's in G minus alpha. This is high linearity, because if it is true for an h in T of R is a real form of T, so it just follows that this is true if you take this up, right? So then T of E alpha is in G minus alpha, and it's not 0. G minus alpha is one-dimensional, so tau G alpha is G minus alpha. And here I go. And the second thing that we will need is that any element in the real group is of the form W is a restriction of some sigma with phi, where phi is an inner automorphism preserving T and commuting with. Why is this true? So we have a formula for how a reflection determined by a simple root is, and we know that the elements of the the well group are generated by reflections determined by physical. So W is a product of reflections. And we know that each of these reflections is of the form exponential if join halves is y and f. This was a proposition for a factor of say chapter 1. Now,
This is restricted to VR, right?
yeah,
Because it's about
yeah. Then now is real form. So in particular, it is an automorphism of the realification of the algebra. Well, I haven't done that this fixes C, but seems like it obviously fixes C prime, so it must fix C, right? I'm not sure about that part. What? I'll check. That these elements fix C. Was it part of the proposition?
I think I mentioned that in the first chapter, but it's true. This is the.
But now consider this.
I fixes T.
Oh, that R comes from an isomorphism that fixes T.
Yeah.
So what he was asking is, that exponential fixes T. And that's true.
Yeah.
Fixes T.
Right. Is my for this exponential, right? That fixes T. I think says said it. So we are not going to try to do it now. Consider the conjugation by tau. Then we have that this is tau exponential as this is the conjugation, we can take the taus inside, take it as a representation. But this is conjugation in a set of matrices, so it is just the same as conjugation inside, right? Because it adds. So this is exponential of tau, the adjoint of pi times en minus fi, minus 1. And now this is the same as the exponential of the adjoint of tau pi times. This is just equals tau of x tau minus 1 of y. It's tau of x, right? So then we have this, we can take the pi halves out, using the formulas that we have for how this tau acts on a basis. We have that tau of this y is minus fi, and tau of minus fi is this y. So then we end up just with the exponential of the adjoint 5 halves is y minus fi, which finally this is just this y, so it commutes with this tau, right? So now we are able maybe finish this session. Now we are able to show that.
Sorry, you didn't mean that fixes t. You meant that leaves t invariant, right?
Yeah, leaves t.
Okay.
Yeah,
Sorry.
sorry.
I was because I heard you a couple of times saying that, and
Yeah,
couldn't
it leaves t
understand.
invariant.
Okay.
Yeah, it's
Yeah.
because it doesn't make sense to make phi act on the roots.
Yeah. Sorry.
Okay.
Then we are able to put the result that we wanted to. This theorem. Existence of compact forms, real forms, which says that tau constructed as before is a compact real structure. And by this, we just mean that fixed tau is compact, right?
Yeah.
So yeah, how do we do this? The first step is to show that the corresponding Hermitian form preserves the root space decomposition. And for this, we will just use this proposition 2 that we just proved, plus the properties of the root space decomposition with respect to the Killing form. So we have that H tau of t and g alpha. It's the same of minus b t minus alpha because of this proposition 2. And we know that this is 0 by the properties of the Killing form, right? And we have that if we take two root spaces, alpha and beta different roots, and that this is minus b g alpha with g minus beta, which this is 0 if alpha minus beta is different to 0, but this is always true because we're taking different roots here. So the root space decomposition is orthogonal with respect to H tau. So, in order to check that H tau is positive definite, we will just have to check it on the different root spaces, right? So, the first step of the proof, we need to prove that H tau restricted to G alpha. This was how do we do this? First, we will prove it for simple root spaces. So H star of P sub I, it's 2 times the norm of alpha sub I squared, which is greater than 0. This is because of the properties of the system of canonical generation. So tau is positive definite in simple root spaces. And to show it in general, we will use this last proposition, which is if alpha is an arbitrary root, there exists an element of a Will group taking such that W transpose of alpha equals alpha slack. This is because the wave group acts transitively on the set of roots, right? So now we use this last proposition. And we can write this W as the restriction to tau far for an integral automorphism limit T invariant and commuting with that. So yeah, then P of P alpha, this is the same of G of this I restricted to the apparent transpose minus 1 of alpha psi because this was a proposition in chapter 1, I think, but this is just G of the transpose minus 1 alpha I. Oh, sorry, this is alpha I here, and this is by definition G of alpha, right? So we have an inner automorphism taking our simple root to the root that we want. This is isomorphism. So an isometry for this tau, because this is automorphism and it commutes with tau, as we saw in the beginning. So H tau restricted to the alpha is positive. And lastly, we are going to prove that H tau of P It's positive definite. And for this, this is easy. You just have to take an h in the real form of t. Then this how h is minus b of h minus h. Again, by proposition to section 1. But this is b of h, and we know that the killing form defines an inner product on t of r. So this is greater than 0. And t of r is a real form of t. Our inner product is positive definite on the real form, and then h star is positive definite on the whole of t. As the root space decomposition was orthogonal with respect to the inner product, we have shown that it's positive definite on each root space, and on t, we have that h star is constant. Finishing this. Maybe in the last 10 minutes I will write a quick example on how we find a real form of something. So take, for example, G equals S7C. T as a maximal torus of algebra, you can take the diagonal matrices with complex centers of phase 0. Its real form is diagonal matrices of phase 0 with real coefficients. As a wheel chamber, we can take the diagonal matrices of phase 0 real coefficients such that its coefficients are ordered. And then we have that for this choice of wheel chamber, the positive roots are the xi minus xj, where I'm meaning by xi and xj the I and j projection of these diagonal matrices, and then simple roots are the xi minus xi plus 1. So then one can compute the canonical system of generators. As this. These devices are of this form. They have a center block, which is 1 minus 1 on the diagonal. Well, sorry, these devices. These devices are of this form. they have a 1 directly above the diagonal, and the FIs are different. They have a 1 directly below the diagonal, right? Yeah. This is the canonical system of generators with respect to D. So we have already seen that the split real structure corresponding to this, which is just taking this to this and making it antilinear. It coincides with the, on the basis with the conjugation of matrices, so it's just the conjugation of matrices. And the wave evolution is given by taking x to minus s transpose. We have to take this to minus phi, so it's just fi to minus ei. It coincides with the conjugate transpose, and the transpose of this is itself, and you just take the minus sign, so there's one to minus the other, right? Coincides in basis, so it has to be the same outcome. Thus, the map taking x to minus x conjugate transform is a compact real structure of SMC. If you remember, the real form corresponding to this was SNR. And here, the corresponding compact real form is SUN, which are the matrices, complex matrices such that x equals minus x conjugate transpose, which of course, once we have seen that this is indeed a real structure, we could have proven because this is the real alpha compactbility, right? So with this, I think I'm done for today. And next session, we will start seeing that the conjugacy classes and how one can find a representative of the conjugacy classes commuting with this power. So yeah, that's about it. I'm going to stop the recording and see you in 2 weeks.